Hey there, pre-AP kids. You're going to want to start off by pausing the video and copying down this board. We're going to start off simple. All right, and simple math's a good place to start. So, let's make sure that we can just count how many atoms are in a molecule. You write down everything that I write down. That's sulfur trioxide, as I'm sure the first thing you thought of when you saw it. And I want to know how many atoms total are in the molecule. I'm not talking about Avogadro's number atoms. All right, I'm just talking about the number of atoms you see. Here's what I see. I see 1 sulfur. I see 3 oxygens for a grand total of how many atoms? There's 4. There are 4 atoms in this molecule. Let's do another one. Let's take a look at palladium. 2 acetate. Now, most of y'all thought that this was very simple, and that's good. Realize that if I give you a name like this, which most oftentimes I will, that don't start trying to count them by looking at the name. We need to translate into a formula, which you're really good at because you've already been tested on it. Palladium is Pd. What's acetate? C2H3O2. Hey, what type of compound is this? Which is the question I should have asked you first. What type of compound? Ionic. Only ionic uses Roman numerals. What's palladium's charge here? All right, +2. That's what the Roman numeral tells us. Acetate, if you look on your polyatomic list, is -1. The values are different, so we'll crisscross. Of course, this is all review. I just wanted to remind you that your new assignments will ask you to do this quite a bit still. And here's what we get. My question is the same. How many total atoms are in one molecule of palladium-2 acetate? Now, we've got parentheses here. The distributive property is in effect. This means that I've got 2 acetates. That means that compound is totally repeated twice. In other words, there's 4 carbons, 6 hydrogens, and 4 oxygens all together. Do you see that? How many palladiums are there? Just 1. That number outside the parentheses, that extra subscript, doesn't affect the palladium. So what's the answer to the question? How many total atoms are there? What'd you get? 15 is what I get. You try one. Keep the answer to yourself. Figure out how many atoms are in that molecule. What number do you get? 32. Good. We had an argument last class. Yeah, 32 is what I get. I get 7, 5, 4, 4, 12. For a grand total of 32. Any questions on counting atoms? This isn't really a leeway into today's skill. This is going to be used for lots of as a step to lots of skills over the next many months. but we will be using it for the oxidation states that we're studying today. Write this down. That's lithium sulfite. As the whiteboard that you copied down at the beginning of this lecture stated, there's some elements that we are no longer going to trust, that the periodic table can simply tell us their oxidation state based off their location. We need to be able to always calculate the charge of everything in a compound, and there's a set protocol to do it. But before we start, we need to understand a basic concept of compounds that we've said before, but are going to think about in a new way. What is the overall charge of lithium sulfite? Neutral. Because the overall charge of all compounds are neutral, unless you can see that a charge has been assigned because some form of the octet rule has been broken. But our assumption for a bunch of units now has been that a net charge of 0 exists in all of our compounds. Here's how we're going to identify the charge of each individual atom of the compounds. I'm going to start off by making a list of what we're dealing with. Lithium, sulfur, oxygen, and then I'm going to count atoms like we did a moment ago. What are my 3 numbers? Now guys, the moment I write down a number that doesn't agree with your brain, sir, where'd you get that number from? Don't just think it and keep it to yourself. If you've got a question, someone else has that same question. Help everybody out and ask. What we're going to do with all we've done is count so far is we're going to multiply these numbers by the oxidation states. Now, I draw these boxes because we're going to be putting a bunch of numbers on the board, but the whole point of the exercise is to figure out the charge of each thing. And that's what we're going to be putting in the boxes. All right? I want you to know where the answer lives instead of being distracted by all the work. Now, I said in the boxes we're going to put oxidation states. We already know some of their oxidation states. Some of these elements we trust. What is lithium's charge? Go find it. Don't just take your classmate's word for it. What is lithium's charge? +1. +1. There he is. Do we trust sulfur? Not anymore. What's oxygen's charge? -2, because he's over there in group 16 and he's not on my whiteboard over there of elements that will stab us in the back. Let's run these numbers. We've got some math set up here. It's pretty simple math. 2 times +1 equals +2. I'm going to keep really worrying about these charges. That's kind of the whole point of what we're doing. 3 times -2 equals -6. Everybody cool? Here's what we need. We need all 3 of these numbers to have a grand total of 0. And right now they don't. What number do these 2 numbers come out to right now? Now, if you can't see the -4, because some of us have issues with integers, I've got great news for you. Under no circumstance will I ever take your calculator away from you. So, when you get to this point, if you can't see that these 2 numbers are currently giving you a -4, then add them together in the calculator. 2 plus -6 equals -4. -4 is not what we need. We need 0. What missing number here? Not just 4, positive. That's the missing number. And now we can figure out the actual number that we're really missing, because we're trying to fill in the squares. 1 times what equals +4? This is beryllium sulfate. I'm going to list the individual elements so that I can find the individual oxidation states. I need to count them. What are the three numbers if I count them? Everyone cool with 114? We're going to multiply them by their oxidation states. Are we certain of beryllium's charge? Yeah, what is beryllium's charge? Again, if you don't know where a number comes from, you need to be screaming at me. Are we certain of sulfur's charge? We're not. Are we certain of oxygen's charge? What is it? -2. Let's run this data. 1 times +2 plus 2. 4 times -2. Don't sneeze on the video just to be famous, all right? What number are we at right now? We're at -6. -6 is not the right number. We need to be at 0. What missing digit can turn that -6 into a 0? +6. All right, now notice how I fill the numbers in. I'm making the charge true, and then I'll take a step back to fill in the square. The oxidation state. 1 times +6 gives me that number that we're supposed to have. The oxidation states are in the squares. The numbers on the outside is just our work. It's what you could be doing in your head to figure out the squares. It's like when you do long division and you have all those do y'all still do long division? Bad analogy then, I guess. That was a good teaching tool like 20 years ago. What? Okay. Let's do another one. New compound. This compound comes from Australia. Yes, it's an Aussie. Aaron liked it. Aaron thought it was funny. Let's list our parts. Gold, selenium. What are the numbers? 2 and 1. Which one are we certain of? Selenium. What is selenium's oxidation state? -2. Is that a question? Alan, no. Well, yeah. You pass. Yes. You did that on purpose. 1 times -2. -2. All right, so I'm just at -2. I'm trying to get to a 0. So what does my other one need to be? +2. Two times what is +2? +1. Let's go through the same steps. What are my two numbers? 3 and 8. We're going to multiply. We want oxidation states. Which one are we sure of? Hydrogen. 8 times plus 1 is plus 8. What's the other number that we need? Minus 8 to get to 0. Everybody cool with that? I'm sure you see our problem. Make yourself a note, like a big, like not a little note, a big note added to your notes that oxidation states don't have to be whole numbers. Oxidation states do not have to be whole numbers. That's whole with a W at the beginning of it. With that said, what we need to happen is 3 times something to equal negative 8. How do you find that out mathematically? You divide negative 8 by 3. Now, if you didn't know that right away, and you were like, well, I was going to divide 3 by negative 8. Cool, do it wrong. But just make sure, I'm not saying do it wrong and walk away from the problem. Do it wrong, and whatever wrong number you get there, just always check the number you put in. Just make sure that 3 times whatever you decided on does equal negative 8. And if you did invert them, you'd find out right away that no, that's not right. But if I do 8 divided by a negative 3, all right, and there's actually 2 ways to do this. All right, you can go like that and just leave it. However, my online assignments don't have fractional answers. So, while that is beautiful and acceptable, we're going to go negative 2.67-ish. And you can check your work. This times this does equal almost that. We rounded, but we had to. Want to see another thing? Yes, you do. Here's a new compound, rubidium carbonate. However, I've changed his charge. Now, we said that our compounds form in order to be neutral. However, you are very accustomed to there being compounds that are not neutral because you had to memorize charges of other things. For example, if I say, what's the charge of sulfate? All right, well, that's S's and O's with a charge of -2. Here's RB's, C's, and O's with a charge of what? -1. This compound is not neutral. This compound's anionic. The only thing that changes about the work we're going to do is when we add up our numbers and we try to hit a number, it needs to be 0. Well, not this time. This time it needs to be -1. Let's do our work. Rubidium, carbon, oxygen. The numbers are 1, 1, 3. Let me know if you disagree with anything I do. We need oxidation states. I'm certain that rubidium is beautiful. I'm certain that oxygen is 1 times +1 is +1. All right, that's a good problem to have to do in creative. 1 times 1. 3 times -2 is. All right, now let's see where we're at right now. If I had a calculator, because I didn't trust my integer skills, and I put 1 plus -6, I would get -5. I need a -5 to really be a -1. What can I add to my number line here to make that true? One times +4 is +4, and now I've got my oxidation states of everybody. People at home, pause the video, copy down the problems, solve them, then unpause. Due to time constraints, I'm going to slowly start just putting work up here. Keep working, and you can glance up and see if what you did matches what I do. What's the name of this compound here? Nonine. It's nonine. Realize that on a test, I could just say, what are the oxidation states of each part of nonine? Just like that. And you'd have to write C9H16 before you could get started. So keep in mind, as I said yesterday, that everything we've done previously is important. Hydrogen's got his +1 that we're sure of, so we needed a -16 to balance it out. This was a fractional answer because you can't make it work with whole numbers. For my last one here, we don't have a charge of 0. We have a charge of -2, so just alter the number you're trying to get to. All right? Niobium was the one that we were unsure of. When we ran everything else, we had -10. To get a -10 down to -2, like I'm supposed to, it took +8 to do it, giving niobium an oxidation state of +4.